Every detail in this story comes from real scientific research and observation. A herd of reindeer scatters in every direction at once, and no one nearby can explain why. 800 kilometers from the center of it all, a window shatters in a house that felt no earthquake, heard no storm, saw nothing but a flash of white light on the horizon. A man is knocked off his porch by a wind that seems to come from nowhere. Trees fall in every direction at once, in a pattern that will take scientists more than 60 years to fully decode. 2,000 square kilometers of forest lie flattened, trunks pointed outward like the spokes of an enormous wheel. And at the center of that wheel, nothing? No crater, no hole torn into the earth, no obvious wreckage of any kind. For 3 nights afterward, the sky over Europe refuses to go fully dark. People in London read newspapers outdoors at midnight by a strange, lingering glow. Barometers in England twitch and dip, registering a pressure wave that has just traveled the entire circumference of the planet. Seismographs across Eurasia jump at the same instant, recording an impact whose source, for decades, no one can locate. Somewhere in Siberia, something arrived, or something exploded, or both. No fragments are ever found at the center, no metal, no stone. Just flattened trees, radiating outward from a point in the sky, as if the forest itself had been struck by something that never touched the ground. This is the story of the Tunguska Event, the largest explosion in recorded history caused by an object from space, an event with the destructive force of hundreds of nuclear weapons, and a mystery that modern science is still piecing together, one clue at a time. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Everything in tonight's episode is drawn from real seismic records, real eyewitness testimony, and real scientific research conducted over more than a century. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. In the early morning hours of June 30th, 1908, in a remote stretch of central Siberia, the sky did something that no one alive had ever recorded before. A rocky or icy fragment, likely no larger than a large office building, entered Earth's atmosphere at a velocity of roughly 15 kilometers per second, more than 50 times the speed of sound. It never reached the ground. Instead, somewhere above the Podkamennaya Tunguska River basin, it released more raw energy in a few seconds than any natural event modern instruments had ever measured before, or would measure again for more than a century. The region where this happened was, and still is, one of the most sparsely populated places on Earth. The Central Siberian Plateau spreads across an area larger than the entire landmass of Western Europe, a raised expanse of ancient volcanic rock laid down hundreds of millions of years earlier, now covered almost entirely by taiga, a biome of coniferous forest, wetland, and slow-moving rivers that circles the northern hemisphere in an unbroken band. Winters here can fall below -50 degrees Celsius. Summers, brief and intense, bring long days of nearly continuous light and swarms of insects that rise from the thawed wetlands in visible clouds. It was, and remains, a landscape shaped almost entirely by extremes, inhabited mostly by small communities of Evenki reindeer herders who had lived across it for many generations, moving with the seasons, largely undisturbed by the political changes unfolding thousands of kilometers to the west. That morning began like countless mornings before it. The sun rose early over the taiga in late June, as it does at these high latitudes, casting long amber light across a forest of Siberian pine, larch, and spruce that stretched unbroken for hundreds of kilometers in every direction. The Podkombinaya Tunguska River wound slowly through this landscape, its dark tannin-stained water catching the early light in long, unbroken ribbons as it cut between low ridges of ancient basalt, rock that had itself been laid down by volcanic activity roughly 250 million years earlier, during a period so severe it very nearly ended complex life on Earth entirely. None of that history was visible on the surface that morning. What was visible was simply forest, river, and sky, exactly as it had looked for longer than any living memory could account for. Beneath the forest floor, much of this landscape rested on a layer of permafrost, ground that remains frozen year-round to depths of tens or even hundreds of meters, thawing only in a shallow surface layer during the brief summer months. This frozen foundation shapes nearly everything about how the taiga grows. Trees send roots sideways rather than down. Rivers spread into wide, shallow wetlands rather than cutting deep channels. And the entire ecosystem exists in a kind of prolonged, patient equilibrium with cold that, elsewhere on Earth, would make sustained plant life impossible. It is a slow-growing forest, in other words, built on a foundation that does not easily forget disturbance. In small clearings scattered through the forest, Evenki families were beginning their day. Reindeer grazed in loose herds near riverbanks, where the morning air was cool and still carried the scent of wet moss and pine resin. Smoke rose in thin columns from a handful of camps, where fires that had burned low through the short summer night were being coaxed back to life. Sable and squirrel moved through the undergrowth in search of the last of the previous autumn's seed caches, and somewhere overhead, capercaillie birds called out across the canopy, their low mechanical clicking carrying easily through air, still cool enough to hold sound close to the ground. The Evenki people, who lived across this stretch of Siberia, had by 1908 sustained a way of life built around seasonal reindeer herding for many centuries, moving in small family groups across enormous distances as the seasons changed, following grazing patterns shaped by generations of accumulated knowledge about the land. Their encampments were never intended to be permanent. A family might occupy a given clearing for only a few weeks before moving on, leaving behind almost no trace beyond a faint clearing in the undergrowth and the cold remains of a fire pit. It was, in its own way, a form of knowledge as precise and as hard-won as any practiced in the scientific institutions of Moscow or St. Petersburg, an intimate, closely observed understanding of a landscape that offered very little margin for error and even less patience for those who misjudged it. Roughly 65 kilometers south of what would become the epicenter, a small trading outpost called Vanavara sat along a tributary of the river, a scattering of wooden structures built to serve the fur trade that connected this remote region to markets as far away as Moscow and beyond. Sable, ermine, and squirrel pelts collected across the winter would pass through outposts like this one, carried by cart and by riverboat toward railheads that were, even in 1908, still hundreds of kilometers away. Its residents were mostly still asleep, their homes quiet in the pale early light, though a handful of traders were already stirring, preparing for a day of the same steady, unremarkable business that had defined life at the outpost for as long as anyone there could remember. Further south still, along the Trans-Siberian Railway, hundreds of kilometers from the forest that was about to be transformed. Passengers dozed in their compartments as the train rolled steadily eastward through the vast Russian interior. The railway itself, completed only a few years earlier after more than a decade of construction, represented one of the largest engineering projects the Russian Empire had ever undertaken. A single continuous line stretching nearly 9,000 kilometers from Moscow to the Pacific coast, built specifically to bind together an empire so vast that entire provinces could rise, farm, trade, and fall silent again without word reaching the capital for months. The passengers aboard that morning's eastbound service were, in most respects, unremarkable. Settlers moving toward new farmland opened up by recent land reforms, merchants following the fur and timber trade, a handful of low-ranking officials assigned to postings so remote that the assignment was, in practice, a form of exile. None of them would feel anything unusual that morning. The event about to unfold was still hundreds of kilometers to the north, well beyond the reach of anything happening along the rail line, though within the hour, several of them would notice the ground shudder faintly beneath the train and would spend the rest of the journey debating, without resolution, what might have caused it. Closer to the center of what would soon become the blast zone, in a small encampment along a bend in the river, an Evenki herder named Bayan was already awake, according to accounts gathered decades later by researchers who traveled into the region specifically to record the memories of the event's last living witnesses. Bayan had risen before sunrise to check on a small herd grazing near the water, a routine repeated every morning of his adult life. His wife and 2 young children were still asleep in the family's tent nearby, along with an elderly relative who had traveled with them since the previous winter's gathering of several extended families near a frozen tributary further north, a seasonal meeting point where marriages were arranged, news was exchanged, and the coming year's migration routes were quietly negotiated among the camp's elders. Bayan noticed nothing unusual in the sky that morning. What he noticed first, according to those later accounts, was the reindeer, all of them at once lifting their heads from the grass and beginning to move, not in the direction of any predator or sound he could identify, but away from something behind them, to the northwest, that he himself had not yet seen. He would later describe, in testimony gathered by Soviet ethnographers decades afterward, a brief instinctive unease at the sight, not fear exactly, but the kind of quiet attentiveness that came from a lifetime spent reading the small, wordless signals animals give before something changes. He turned to see what had unsettled them. There was no reason in that quiet hour for anyone to look up. Nothing about the morning suggested that anything unusual was approaching. The sky was reportedly clear over much of the region, the kind of pale, cloudless blue that summer mornings in Siberia often bring. A light wind stirred the tops of the pines. The forest remained as it had for thousands of years, vast, quiet, and entirely unaware of what was falling toward it out of a clear June sky at a speed no living thing on the ground could have outrun. By 1908, the Russian Empire had held nominal control over this stretch of Siberia for roughly 300 years, since fur traders and Cossack expeditions first pushed east across the Ural Mountains in the late 16th century in search of sable pelts, valuable enough to fund entire military campaigns. Control, in this context, meant something quite different from the way it might have applied closer to Moscow or St. Petersburg. Across most of the central Siberian plateau, imperial authority existed mainly as a distant, occasional presence, a tax collector passing through once a year, a trading license issued at a regional outpost, a garrison town many days' travel away. For the Ivanki families living and moving across this landscape, the empire that claimed the land was in practice almost entirely absent from daily life, a fact that would matter a great deal in the days following the coming explosion, when there would be no telegraph line, no rail connection, and no official channel capable of quickly carrying word of what had happened to anyone outside the immediate region. That isolation, more than anything else, is why an explosion large enough to be felt on the other side of the planet would remain, for nearly 2 decades, a story told only in fragments, rumors passed along trade routes, a handful of newspaper clippings, and the memories of people who had witnessed something extraordinary but had no means of proving it, and in some cases, little desire to try. Above the atmosphere, unseen by any human eye, the object that would soon change this landscape forever was already deep into its final approach, and the journey that had brought it there had likely begun long before anything resembling a human civilization existed on Earth. Most objects capable of producing an event on this scale originate in one of 2 places within the solar system. Some are fragments of the asteroid belt, a wide ring of rocky debris orbiting between Mars and Jupiter, leftover material from the solar system's formation roughly 4.5 billion years ago that never coalesced into a full planet. Others are fragments of comets, icy bodies that spend most of their existence in the solar system's distant outer reaches before occasionally being nudged by the gravity of a passing star or the slow gravitational influence of the outer planets onto a long path back toward the sun. Both kinds of objects, once dislodged from a stable orbit, can spend anywhere from thousands to millions of years drifting on paths that gradually shift under the gravitational influence of the planets they pass, until, by the extraordinarily long odds involved, one such path happens to intersect the orbit of Earth at precisely the moment Earth itself arrives at that same point in space. That is what happened on the morning of June 30th, 1908. Whatever the object was, asteroid or comet, a question modern science still has not fully resolved, it had spent an unknown span of time following a path that on that particular morning crossed paths with a small, water-covered planet moving through its own orbit at nearly 30 kilometers per second, and the 2 arrived at the same point in space within the same fraction of a second. The orbital mechanics involved in an encounter like this are governed by the same basic laws that keep every planet, moon, and asteroid in the solar system moving along predictable, if occasionally intersecting, paths, laws first described in complete mathematical form by Johannes Kepler in the early 17th century, and refined further by Isaac Newton's description of gravity later that same century. Every object in the solar system follows an elliptical path around the sun, its speed and trajectory determined by the combined gravitational pull of the sun and every other significant body nearby. For most asteroids, this means an orbit that stays safely within the asteroid belt, undisturbed for millions or even billions of years. But a small fraction of these objects, those that pass close enough to a large planet like Jupiter, or are struck by a collision with another asteroid, can have their orbits nudged just enough to become what astronomers call Earth-crossing objects, bodies whose paths intersect the orbit of Earth itself at least twice during every trip around the sun. Even for an Earth-crossing object, an actual collision remains extraordinarily unlikely on any single pass. Earth is, from the perspective of an object hurtling through the emptiness of space, an almost impossibly small target, a sphere roughly 12,742 kilometers across, moving through a solar system that spans billions of kilometers in every direction. It is only across very long timescales, with an object crossing Earth's orbital path again and again over thousands of years, that the odds eventually catch up. On the morning of June 30th, 1908, after what may have been thousands of such crossings over an unknown span of time, they finally did. Events of this scale are, by the standards of Earth's long geological history, exceptionally rare. The geological record preserves evidence of a small number of impacts large enough to have reshaped entire regions, or, in the most extreme cases, altered the course of life on the planet. The Chicxulub impact off the coast of what is now Mexico, some 66 million years ago, widely understood to have contributed to the extinction of the non-avian dinosaurs, remains the most consequential example known to science, though it involved an object many times larger than whatever was now approaching the Siberian taiga. Events on the scale of what was about to happen over the Podkamennaya Tunguska River, by contrast, are estimated to occur on average only once every few hundred years, rare enough that no scientific instrument in human history had ever been positioned to observe one directly, and rare enough that when this one finally arrived, an entire generation of scientists would spend the rest of their careers trying to understand exactly what they had missed. It was moving faster than any sound could travel, faster than any warning could arrive. By the time anything in the sky above the taiga became visible to human eyes, there would be no time left to react, only time enough to witness. At the outermost edge of Earth's atmosphere, roughly 100 kilometers up, air is thin enough that it offers almost no resistance at all. Satellites and spacecraft pass through this region routinely, without so much as a shudder. But an object moving at 15 kilometers per second does not experience that thin upper air as empty space. At that velocity, even a handful of air molecules per cubic centimeter are enough to begin generating friction and compression, the first faint traces of a process that would, within seconds, become one of the most violent releases of energy the region had ever witnessed. High above the taiga, invisible from the ground, the leading edge of the object had already begun to glow a dull, deepening red, the first sign of an object about to become, briefly, one of the brightest things in the sky. The forest below continued in its stillness. Smoke from the morning fires continued to rise in thin, unbroken columns. Near the river, Bayan continued watching his reindeer move away from him, still without understanding why, the animal's instinct registering something that his own senses had not yet caught up to. Somewhere behind him, inside the tent, his children slept on, unaware that the last ordinary morning any of them would ever fully remember was already, in its final seconds, coming to an end. And far above, closing the last few hundred kilometers of a journey that had likely begun before the first cities on Earth were built, something enormous and largely invisible was already beginning to glow. What happened next unfolded in less than a minute, but its effects would be measured, studied, and debated for more than 100 years afterward. According to Soviet-era interviews conducted with surviving witnesses in the 1920s and 1930s, the first sign came as light, an intense bluish-white brilliance that some described as brighter than the sun, appearing suddenly in the northwestern sky. Witnesses as far as several hundred kilometers away reported seeing what looked like a second sun rising in the wrong part of the sky, moving. Semenov, a farmer at the Vanavara trading post, roughly 65 kilometers south of the eventual epicenter, was sitting on the steps of his house when the sky brightened. He later described the sensation of intense heat on his exposed skin, heat so sudden and severe that he believed his shirt had caught fire. Before he could fully react, he reported being thrown from where he sat, landing several meters away, momentarily losing consciousness. When he came to, he found that his shirt had not in fact burned, though the heat he had felt had been real enough to leave him certain in the moment that it had. His neighbor, seated near him on the same porch, would later describe the sky as having split apart, with fire that seemed to cover the entire northern horizon. Both accounts, recorded independently by researchers who interviewed them years apart, described the same sequence of events in the same order. First the light, then the heat, then, several long seconds later, a sound and a wind violent enough to knock a grown man from where he sat. In the hours that followed, word of the event spread through Vanavara and the surrounding trading posts, largely by rumor, carried between households by whoever happened to be traveling that day. Without any means of confirming what had actually happened to the north, explanations varied widely. Some assumed a powder magazine at a distant garrison had exploded. Others assumed, more fearfully, that the strange light and sound were signs of some coming catastrophe, a belief that persisted in parts of the region for years afterward. Almost no one at the time guessed the true cause, in part because nothing resembling it had ever been recorded happening on Earth before, at least not within living memory or written record. These accounts, collected decades after the event by researchers who traveled deep into the taiga, specifically to interview aging witnesses, form the backbone of what scientists know about the human experience of that morning. They are not isolated. Similar reports came from herders, traders, and travelers scattered across a region spanning hundreds of kilometers, people who had no way of communicating with one another in the moment, yet whose independent accounts describe nearly identical sequences of events: a flash brighter than anything they had seen before, a wave of heat, and then, after a pause long enough for some witnesses to believe the danger had passed, a violent concussion of sound and wind. Further away, at the town of Kirinsk, more than 300 kilometers from the eventual epicenter, residents reported a sequence of 10 to 15 distinct concussive booms, evenly spaced, rolling across the sky roughly 20 minutes after a bright flash had been seen to the north, an experience so unusual that several residents later gave written statements comparing it to distant cannon fire, though none could identify a plausible source. At Kansk, along the Trans-Siberian Railway itself, station staff reported a sudden tremor passing through the ground, strong enough that some at first assumed a train had derailed nearby, before quickly realizing that no track ran close enough to explain what they had felt. That delay between the light and the sound is itself a measurable piece of evidence. Light travels fast enough to be, for all practical human purposes, instantaneous across these distances. Sound does not. It moves through air at roughly 343 meters per second under normal conditions, meaning that a witness located, for instance, 100 kilometers from the blast would have seen the flash immediately, then waited nearly 5 full minutes before the sound and shockwave finally reached them, an agonizing gap that several witnesses specifically recalled in later testimony, describing those in-between minutes as some of the most unsettling of their lives, not knowing whether whatever had lit the sky was still coming toward them. A riverboat captain navigating the Angara River, more than 500 kilometers to the southwest, later gave a statement describing the sky changing color in stages as the object approached and disintegrated, beginning as a point of white light, little different from an ordinary star, then rapidly brightening and shifting toward a deep, saturated blue-white before the flash reached its peak intensity, and the sky itself, in his words, seemed briefly to catch fire along the horizon. That progression of color is itself scientifically meaningful. The shift toward blue-white indicates rising temperature, since hotter objects radiate light at shorter, bluer wavelengths, a relationship known to physicists as black-body radiation. A dull red glow corresponds to a relatively cooler few thousand degrees. The blinding blue-white witnesses described corresponds to temperatures reaching well into the tens of thousands of degrees, consistent with the extreme adiabatic heating generated in the object's final seconds of atmospheric entry. What these witnesses were seeing, though none of them could have known it at the time, was the final phase of a process now well understood by modern astrophysics: the atmospheric entry and disintegration of a large near-Earth object. When a body of rock or ice enters Earth's atmosphere at cosmic velocity, in this case, an estimated 15 kilometers per second, or roughly 54,000 kilometers per hour, it does not simply fall like a stone. At that speed, the object compresses the air directly in front of it so rapidly and so violently that the air itself heats to temperatures exceeding those on the surface of the sun. This is not friction in the way most people imagine it. It is adiabatic compression, air molecules crushed together so quickly that they have no time to disperse the resulting heat, creating a superheated shock wave that races ahead of the object itself, a wall of plasma reaching temperatures upward of 20,000 degrees Celsius, more than 3 times hotter than the sun's visible surface, though it lasts only a matter of seconds. That shock wave is what witnesses would have seen first, not the object but the column of superheated, glowing air being pushed ahead of it, brighter than the midday sun, visible from hundreds of kilometers away, even in full daylight. For comparison, even the brightest conventional lightning bolt reaches temperatures of only around 30,000 degrees Celsius for a duration measured in millionths of a second. The column of compressed air ahead of the Tunguska object was, by some estimates, comparable in temperature, but sustained across several full seconds as the object continued its descent, long enough for the light and heat it generated to be felt as a physical sensation on exposed skin more than 60 kilometers away, as Semenov's own testimony would later confirm. As the object continued its descent, the same forces that generated that heat began tearing it apart from the outside in. Unlike a solid steel sphere, the Tunguska object, whether icy comet fragment or loosely bound stony asteroid, was almost certainly a weaker, more porous body, riddled with internal fractures and pockets of lower density, the kind of structure common among smaller asteroids and cometary debris. As atmospheric pressure on its leading face increased faster than the object's own structural strength could withstand, it began to fracture, then crumble, then break apart entirely in a cascading process that released its enormous kinetic energy in one final, catastrophic burst. The 10 to 15 distinct booms reported by witnesses in Kairensk are, in fact, consistent with what modern researchers understand about how large airbursts unfold. Rather than a single, instantaneous detonation, an object of this size is more likely to have broken apart in a rapid cascade. An initial major fragmentation followed, within fractions of a second, by a series of smaller secondary bursts, as each resulting fragment reached its own individual breaking point under the same immense aerodynamic pressure. Each of those secondary fragmentation events would have produced its own distinct pressure pulse, arriving at a distant listener's ears as a separate, countable boom rather than a single prolonged roar, an acoustic signature that closely matches multiple well-documented smaller airbursts recorded by modern infrasound and video instrumentation, including the 2013 Chelyabinsk event, where dashcam footage captured a strikingly similar sequence of a bright flash followed by several distinct, separated concussions rather than one continuous blast. This is what scientists now call an airburst, an explosion that occurs not on impact with the ground, but in the air itself when an incoming object's structural failure releases the whole of its stored energy, energy equal to its mass multiplied by the square of its extraordinary velocity, almost instantaneously, at altitude. It is the same basic physics that governs why a water balloon dropped from a great height sometimes bursts apart in mid-air before it ever reaches the ground if the pressure of the fall exceeds what its outer skin can hold, except that here, the balloon was a mass of rock or ice roughly the size of an office building, and the pressure involved was generated by a speed 50 times greater than the speed of sound. For Tunguska, that altitude is now estimated, based on decades of analysis of the fallen tree pattern, to have been somewhere between 5 and 10 kilometers above the ground, roughly the cruising altitude of a modern passenger jet. At that height, the resulting explosion released energy equivalent to somewhere between 10 and 15 megatons of TNT, making it, by most estimates, several hundred times more powerful than the atomic bomb detonated over Hiroshima in 1945, and among the largest explosions, natural or artificial, ever recorded on Earth. To put that figure in perspective, it is comparable to the combined explosive yield of every conventional bomb dropped by all sides during the entirety of the Second World War, released in a single instant 5 to 10 kilometers above an otherwise unremarkable stretch of forest. This single fact, that the explosion occurred in the air rather than at ground level, is the key to one of the event's most persistent mysteries: why, despite unleashing forces capable of leveling a major city, the Tunguska Event left behind no crater at all. An object striking the ground directly excavates a bowl-shaped depression, throwing up debris and leaving behind fragments of the impactor itself, often for scientists to study centuries later. An airburst does something entirely different. Because the explosion happens kilometers above the surface, its energy radiates outward and downward in the form of heat, light, and a shock wave, rather than being concentrated into a single point of contact with solid ground. The shock wave alone was enough to do what a direct impact might have done to the forest, without ever touching it. As the pressure wave expanded outward from the point of detonation, it moved faster than the speed of sound, striking the forest below with enough force to snap full-grown trees at their trunks, not randomly, but in a pattern that radiated outward from the blast in almost every direction, like ripples frozen in the moment they were formed. The physics of that snapping is a matter of overpressure, the difference between normal atmospheric pressure and the sudden brief spike in pressure created by a shock wave passing through. Human structures and living trees alike can typically withstand only a few pounds per square inch of overpressure before failing. Near the center of the Tunguska blast, researchers have since estimated overpressures reaching several tens of pounds per square inch, enough not merely to snap trunks, but to strip bark and branches entirely from any tree unlucky enough to be standing near the point of detonation. It is a similar mechanism on a vastly larger scale to the shattered windows and structural damage produced by the Chelyabinsk airburst more than a century later, or to the atmospheric shockwave generated by the 1883 eruption of Krakatoa, an explosion so powerful it was heard nearly 800 kilometers away and circled the globe as a measurable pressure wave multiple times, the only other naturally occurring event in the modern instrumental record, with an atmospheric signature comparable to what the Tunguska explosion would leave behind. 80 million trees falling in the same instant across an area larger than many modern cities. The specific way a tree fails under this kind of lateral pressure depends on both the strength of its trunk and the force applied to its canopy, where the greatest surface area catches the wind of the shockwave. Larger, older trees with thicker trunks but also broader crowns often snapped partway up the trunk rather than being uprooted entirely, while younger, more flexible trees closer to the outer edge of the blast zone, where the shockwave had weakened considerably by the time it arrived, were sometimes merely bent or partially stripped of branches, marking the rough boundary of the area affected by the explosion, a boundary that researchers would later use, together with the more severely damaged inner zone, to help reconstruct the full three-dimensional shape of the blast. At the very center of the blast, almost directly beneath the point of detonation, a small stand of trees was left standing upright, stripped of branches and bark, scorched but not knocked down, because the shock wave at that precise point had been traveling almost straight downward rather than outward. Scientists who mapped this pattern more than half a century later would use it, along with the outward radiating fall pattern surrounding it, to calculate both the altitude and the approximate energy of the explosion with remarkable precision, essentially reconstructing the physics of an event that no scientific instrument had directly recorded. Beyond the forest itself, the effects of the explosion rippled outward across the planet in ways few at the time fully understood. Some of the energy released by the explosion traveled even farther than the audible shockwave in the form of infrasound, pressure waves at frequencies too low for human ears to detect, typically below 20 Hz. Infrasound waves lose far less energy to atmospheric absorption than higher frequency sound, allowing them to travel enormous distances with relatively little decay. Modern infrasound monitoring stations, originally developed to detect nuclear weapons tests, can now pick up large volcanic eruptions, major meteor airbursts, and other high-energy atmospheric events from thousands of kilometers away. No such monitoring network existed in 1908, but the same low-frequency waves the Tunguska explosion generated would almost certainly have been detectable on modern instruments across multiple continents had they existed at the time. A reminder that much of what an event this size actually produced went entirely unmeasured, simply because the tools to measure it had not yet been invented. At weather stations across Britain, sensitive barographs, instruments designed to record tiny fluctuations in atmospheric pressure over time, registered something unusual that morning, a distinct pressure pulse, arriving hours after the event itself, having traveled the roughly 5,000 kilometers separating Siberia from Western Europe at the speed of sound through the upper atmosphere. At several stations, the instruments recorded not one pulse, but two, a first, sharper wave that had traveled the most direct path around the globe, followed some hours later by a second, fainter pulse that appeared to have continued on past Britain, circled the rest of the planet, and arrived again from the opposite direction, having completed nearly the full circumference of the Earth before its energy finally dissipated into the general noise of the atmosphere. For 3 nights afterward, skies across parts of Europe and Asia refused to go fully dark, glowing instead with an unusual persistent brightness after sunset, bright enough in some places for people to read outdoors at midnight without any additional light source. The mechanism behind this phenomenon, only fully understood decades later, involves fine dust and ice particles that the explosion had lofted to extraordinary altitudes, in some cases more than 80 kilometers up, into a layer of the atmosphere cold and dry enough for ice crystals to form on the dust and remain suspended for days. At that altitude, sunlight continues to strike suspended particles long after the sun itself is set below the local horizon, scattering downward and producing a soft, persistent glow across the night sky, a phenomenon similar in mechanism to noctilucent clouds, though on a scale rarely observed before or since. No one at the time connected these scattered observations, the strange glowing nights, the twin pressure pulses on English barographs, the distant flash reported by a handful of Siberian traders, into a single event. A scientist in London reading by an unusually bright midnight sky had no way of knowing that the light overhead originated from dust lofted by an explosion thousands of kilometers away, in a part of the world most Western European newspapers rarely mentioned at all. A meteorologist in Berlin recording the same phenomenon in a weather logbook had no more information than his counterpart in London. A ship's navigator somewhere in the North Atlantic, using the unusually bright night sky to take a set of star sightings he later described as unnecessary given the ambient light, likewise had no way of connecting what he was observing to any single cause. Each observation existed, for the time being, as an isolated curiosity, filed away without explanation, waiting for someone to notice that they had all occurred within days of one another. Russia in 1908 had no seismic or meteorological network reaching into its remote eastern regions, no means of rapidly sharing observations across such vast distances, and, in the years immediately following, far more pressing political upheaval to contend with. It would be nearly 2 decades before anyone traveled deep into the Siberian taiga to see, firsthand, what had actually happened there, and to begin the long scientific process of understanding an event that, even now, continues to reveal new details with each passing decade. The shockwave that flattened the forest was only the most visible of several forces unleashed in those final seconds over the taiga, and its passage left behind evidence that scientists would spend the better part of a century learning to read. At the Irkutsk Magnetic and Meteorological Observatory, more than 800 kilometers from the epicenter, instruments recording the planet's magnetic field registered a disturbance beginning at almost the exact moment witnesses reported the flash in the sky. The needles tracing Earth's magnetic readings on that morning's chart show a sudden deviation, followed by several hours of irregular fluctuation before settling back to normal, a signature strikingly similar to the geomagnetic disturbances produced by high-altitude nuclear detonations discovered independently decades later during Cold War weapons testing. The seismic component of the event, recorded on the primitive mechanical seismographs of the period at stations across Western Russia and beyond, arrived in a specific, measurable sequence that later analysts would use to help pinpoint the location of the blast. These early seismographs, still a relatively new scientific instrument in 1908, work through a simple but effective principle. A heavy suspended mass, largely isolated from the vibration of the ground around it by its own inertia, remained nearly still while the instrument's frame moved with the earth beneath it, and a pen attached to the mass traced the resulting relative motion onto a slowly rotating drum of paper. It was a crude system by later standards, but sensitive enough to register even distant, moderate disturbances, and precise enough to record the passage of time down to the minute. Faster-moving compressional waves, known as P waves, reached the nearest instrumented stations within minutes, followed some time later by slower-moving surface waves that carried the bulk of the seismic energy across greater distances. Because seismic waves travel through solid rock at speeds that can be calculated with reasonable precision, the arrival times recorded at multiple stations, when later gathered and compared decades after the fact, allowed scientists to triangulate backward toward a rough point of origin in much the same way modern earthquake epicenters are located today. It was one of the first pieces of hard instrumental evidence, alongside the Irkutsk magnetogram, that would eventually help researchers confirm both the location and approximate scale of the explosion, long after any living memory of it had begun to fade. Only a small handful of seismic and meteorological stations existed across the entire Russian Empire in 1908, most of them concentrated in major cities far to the west. Irkutsk's observatory, established decades earlier primarily to support navigation and basic weather forecasting for the growing rail and river trade through the region, was among the closest functioning scientific instruments to the blast, and even it sat more than 800 kilometers away, a distance that, for comparison, is roughly equivalent to the entire length of Great Britain end to end. No comparable instrument existed anywhere closer to the epicenter itself, meaning that even the earliest and most direct instrumental evidence of the event came from a station too distant to record anything beyond its most diffuse secondary effects. At the time, the observatory's staff had no explanation for what had briefly unsettled the Earth's magnetic field, nor any clear sense of how the faint seismic tremors they had recorded that same morning might be connected. It would be more than 60 years before researchers, comparing the Irkutsk magnetogram to newer geomagnetic data, understood what they were looking at: the ionized trail of superheated air and vaporized debris, briefly disturbing the upper atmosphere's electric currents on a scale large enough to register at a facility hundreds of kilometers away. Earth's magnetic field is generated deep within the planet by the slow churning motion of molten iron in the outer core, and extends far out into space, where it interacts constantly with charged particles streaming from the sun. Closer to the surface, a layer of the atmosphere known as the ionosphere, stretching from roughly 60 to 1,000 kilometers up, contains a significant population of free electrons and ions, charged particles, capable of conducting electrical current and, under the right conditions, generating their own localized magnetic disturbances. The extreme heat of the Tunguska fireball and the trail of ionized gas and vaporized material it left in its wake as it disintegrated briefly added a dense, highly charged disturbance to this layer directly above the blast site, enough, evidently, to send a measurable ripple through the ambient electrical currents of the ionosphere, registering as a faint but real deviation on a sensitive magnetometer needle more than 800 kilometers away. Closer to the blast, the effects were far less abstract. The handful of Evenki families living closest to the event experienced something no instrument could record: the immediate physical shock of the airburst itself, arriving without warning into an otherwise ordinary morning. Accounts gathered decades later describe tents collapsed by the pressure wave, cooking fires scattered by the force of the wind, and a lingering smell of scorched pine resin that several witnesses recalled persisting in the air for days afterward, carried on whatever breeze moved through the affected region. Reindeer herds grazing within roughly 30 kilometers of the epicenter suffered severe burns from the thermal flash, the same superheated column of compressed air that had thrown Semenov from his porch in Vanavara, but concentrated here at far greater intensity. Even key accounts gathered decades later describe entire grazing herds lost in the initial blast, their carcasses found later with fur singed away on the side facing the explosion, a detail consistent with what scientists now understand about thermal radiation from airbursts, heat delivered not by flame, but by direct radiant exposure, capable of scorching exposed surfaces from kilometers away in a fraction of a second, well before any shock wave arrived. Radiant heat of this kind behaves differently from the heat produced by an ordinary fire, and the distinction mattered a great deal to those trying to understand the blast decades later. A campfire or forest fire transfers most of its heat through direct contact and convection, hot air and flame physically touching or surrounding whatever it burns. Radiant heat, by contrast, travels as electromagnetic energy, much like sunlight, and can transfer significant thermal energy across long distances without any physical contact at all, limited mainly by line of sight and the inverse square law governing how radiation intensity fades with distance. This is why witnesses many tens of kilometers from the blast, far too distant to have felt any wind or heard the sound clearly yet, nonetheless reported a distinct, immediate sensation of heat on any skin left exposed and facing the direction of the flash, radiant energy arriving at nearly the speed of light, well ahead of the slower moving blast wave and sound that would follow. Fires broke out across parts of the forest almost immediately, ignited by that same thermal pulse acting on dry pine needles and resin-heavy bark. Unlike the wind-driven wildfires familiar to the region in dry summers, witnesses describe these fires as starting simultaneously across a wide area rather than spreading outward from a single point, consistent with ignition by a broad flash of radiant heat rather than by burning debris falling from the sky. Because these fires ignited across many separate points at once rather than spreading from a single origin, they also tended to burn themselves out relatively quickly, starved of the sustained wind and continuous fuel supply that allows an ordinary forest fire to travel long distances. Several later researchers have noted that this pattern likely limited the total burned area to a small fraction of the much larger zone affected by the shock wave alone. Later analysis of the site would find scorch patterns on standing tree trunks nearest the center of the blast, evidence of fire that began and was extinguished within moments, snuffed out by the same shock wave that arrived only seconds behind the heat that had started it. The immediate ecological impact extended well beyond the reindeer herds themselves. Birds nesting in the canopy nearest the blast were killed instantly by the combined force of heat and shock wave, their populations in the affected zone reduced, according to later ecological surveys, by a degree not fully recovered for several decades. Fish in the shallower stretches of the Podkamanaya Tunguska River, close enough to the blast to be affected by the sudden pressure change transmitted through the water, were found dead in unusual numbers in the days that followed, though the river itself, fed by a watershed far too large to be significantly affected by a single localized event, showed no lasting change to its broader ecology. Insects, generally more resilient to blast effects than larger animals due to their small size and often sheltered nesting habits, appear to have rebounded within a single season based on later comparisons between the blast zone and unaffected forest nearby. Heat first, then wind, then silence. For the handful of Evenki families living within the affected radius, The physical destruction was compounded by something the scientific record captures less completely: displacement, loss, and fear. Some families lost not only reindeer, but also stores of food and shelter built to survive the coming winter. Bayan's own family, according to the same later accounts that preserved his name, lost most of their small herd in the first minutes after the blast, the animals scattering so completely across the surrounding forest that fewer than half were ever recovered in the weeks that followed. A loss that, for a family whose entire livelihood depended on those animals, represented a hardship far more lasting than the physical damage to the land itself. Rebuilding a reindeer herd after a loss of this scale was neither quick nor simple. Even key herding practice relied on animals that had been raised within a specific herd, familiar with its particular migration routes and social structure. Simply acquiring replacement animals from a neighboring family, when possible at all, meant integrating unfamiliar reindeer into a smaller, disrupted group, a process that could take several full breeding cycles to fully stabilize. For a family already living close to the margin of what the land could reliably provide, a setback of this size could shape the following several years of decisions about where to travel, when to trade, and how much risk the family could afford to take with its remaining animals. Oral accounts collected by Soviet ethnographers decades later, accounts that blend eyewitness memory with the retelling that happens across a generation, describe a lasting reluctance among some community elders to travel near the affected area, a place they came to regard as marked by forces beyond ordinary explanation. Some families reportedly altered their traditional migration routes for years afterward to avoid passing directly through the blast zone, a decision that, whatever its cause, had the unintended effect of leaving much of the fallen forest undisturbed by human activity during the earliest and most fragile stage of its recovery. Bayan and his family, according to the fragments of testimony that survived him, remained in the wider region for the rest of that summer, gradually rebuilding what could be rebuilt before the onset of winter made travel and resupply far more difficult. Later accounts describe the family joining a larger seasonal gathering of Genki households later that year, where the events of that June morning were discussed at length, not as a scientific mystery, but as a shared, unresolved experience that every family present had, in one way or another, felt for themselves. Even can oral tradition, built around generations of carefully transmitted practical and environmental knowledge, had no existing framework for an event like this one. No prior story of fire falling from a clear sky, no established explanation passed down from earlier generations to draw upon. In the absence of any such precedent, explanations that emerged in the years immediately following tended to blend the observably physical with the spiritual, framing the event in terms consistent with broader Evenkin cosmology, in which the sky, the forest, and the spirits understood to inhabit both were seen as continuous with, rather than separate from, everyday experience. It would be more than a decade before anyone from outside that community arrived, asking specific, systematic questions about what exactly had happened, and by then, the story had already begun the slow drift from lived memory into local legend, retold at gatherings in versions that grew, year by year, slightly different from what had actually occurred. What makes the Tunguska event scientifically distinct from nearly every other large impact event in Earth's geological record is not simply its size, but its timing. It occurred within living memory in an era when instruments capable of recording it, barometers, seismographs, magnetometers, already existed and were already operating, scattered in observatories across a hemisphere, And yet, because the event took place in one of the most remote and sparsely inhabited regions on the planet, more than 4,000 kilometers from Moscow, and further still from the scientific centers of Western Europe, its cause remained entirely unknown to the outside world for nearly 2 decades. Russia, in the years immediately following 1908, had little capacity to investigate. The country was, at that moment, still recovering from the aftermath of the Russo-Japanese War of 1904 to 1905, a costly and humiliating military defeat that had triggered widespread civil unrest and forced the imperial government into a series of reluctant political reforms. Scientific institutions, dependent on state funding and stability, to mount any expedition into a region as remote and logistically demanding as Central Siberia, were not a priority for a government already struggling to manage unrest closer to its major population centers. The scattered instrumental readings, the trembling barographs in England, the magnetic disturbance at Irkutsk, the strange bright nights reported from Stockholm to Berlin, were recorded, filed, and in most cases forgotten, treated as unconnected curiosities rather than fragments of a single, enormous event. Russia's scientific institutions had neither the resources nor, in the years that followed, the political stability to mount an expedition into one of the most remote corners of Siberia. The First World War began in 1914, drawing men and resources away from any scientific inquiry that could not be justified as directly useful to the war effort. The Russian Revolution followed in 1917, plunging the country into years of civil war, famine, and administrative collapse that left most of its scientific institutions struggling simply to continue functioning at all. It would not be until the country's political situation had stabilized in the mid-1920s that anyone with scientific training would have the opportunity, the funding, or the institutional support to travel into the taiga and ask, systematically, what had actually happened there. In the meantime, the story of the Great Siberian Fireball survived the way most things survive in a region without newspapers or telegraph lines reaching every settlement, by word of mouth carried along trade routes and river crossings, growing more fragmentary and more difficult to verify with each retelling. A handful of regional newspapers had run brief accounts in the days immediately following the event, based on second-hand reports from travelers passing through affected towns. But these accounts were short, inconsistent in their details, and quickly overtaken by other news. Even further afield, a small number of foreign newspapers picked up brief wire reports describing an unusual fireball and tremor somewhere in the Russian interior, typically buried among minor international items, with little follow-up, since no correspondent had any practical way of traveling to such a remote location to verify the claims or gather further detail. Without photographs, without a named location precise enough to investigate, and without any official Russian government statement on the matter, the story simply had nowhere to go, and within weeks it had largely disappeared from print entirely, surviving mainly in the private notebooks of a handful of meteorologists who had recorded the associated atmospheric effects without understanding their cause. By the early 1920s, when the first Russian scientists began to take a serious interest, they were not investigating a fresh event. They were attempting to reconstruct something that had happened more than a decade earlier, using the memories of aging witnesses and the physical scars still visible on the land itself, scars that, remarkably, the forest had barely begun to heal. The man who would lead that reconstruction was a mineralogist named Leonid Kulik, born in 1883 in what is now Ukraine, who had trained in the earth sciences before the First World War and spent much of the following decade working under difficult, often chaotic conditions as the empire he had been educated in collapsed and reformed itself into the Soviet Union around him. By the early 1920s, Kulik had found a research position with the Soviet Academy of Sciences Mineralogical Museum, a role that gave him access to an extensive archive of reports on meteorite falls collected from across the vast territory of the former empire, a task he approached with the kind of meticulous, almost obsessive thoroughness that would later define his pursuit of Tunguska. It was in reviewing this archive, rather than through any direct contact with witnesses, that Kulik first encountered fragmentary references to an enormous fireball seen over central Siberia in 1908, a handful of old newspaper clippings, a brief mention in a scientific journal, second-hand reports of trees flattened across an area so large that, if accurate, it would represent by far the largest meteorite fall ever documented anywhere in the world. The assumption Kulik carried into the taiga, an assumption shared by nearly every scientist of his era who had studied the handful of confirmed meteorite impacts on record, was that an explosion of this size must have left behind a crater, and somewhere within that crater, fragments of the object responsible. He would spend the better part of his career searching for a hole in the ground that, as it turned out, had never existed at all. Leonid Kulik first heard fragmentary accounts of the Tunguska explosion in 1921, while reviewing old records of meteorite falls across the Russian Empire as part of a broader survey for the Soviet Academy of Sciences. Among newspaper clippings and scattered observatory reports, he found references to a massive fireball seen over central Siberia in 1908, along with second-hand accounts of trees flattened across an enormous area. Convinced that such a report pointed to an undiscovered meteorite of extraordinary size, one that could bring considerable scientific prestige to whoever confirmed and studied it first, Kulik petitioned for years to secure funding and permission for an expedition into one of the most remote and logistically difficult regions of the Soviet Union. Securing that funding was not straightforward. The young Soviet state, still rebuilding its economy and institutions after years of war and revolution, had limited resources to spare for an expedition whose scientific value remained, at that point, entirely speculative. Kulik spent several years gathering additional testimony from anyone he could locate who had witnessed the event or heard first-hand accounts of it, slowly building a case detailed enough to justify the expense and difficulty of an expedition into a region with no roads, no reliable maps, and no permanent scientific presence of any kind. He corresponded extensively with regional administrators and railway officials across Siberia, requesting any recollections or second-hand reports they could gather from residents along the relevant stretch of the Trans-Siberian line, gradually assembling a rough geographic picture of where the felled forest was most likely to be found, well before he ever set foot in the region himself. His first expedition finally departed in 1927, nearly 2 decades after the event itself. Kulik began the journey from Leningrad, first by rail across a significant portion of the Soviet Union, before reaching the point where the railway itself gave out, several hundred kilometers still short of the blast zone. The team traveled by train as far as the rail line extended, then transferred to horse-drawn cart for the next stage of the journey, and finally continued on foot and by boat along the Podkamenia-Tunguska River, through terrain with no roads, few reliable maps, and a local population still hesitant to guide outsiders toward a place many regarded with unease. Local guides, drawn from among the Evenki families still living in the wider region, proved essential to the expedition's progress, possessing an intimate knowledge of the terrain, river conditions, and seasonal hazards that no map available to Kulik could have provided. Several of these guides, according to Kulik's own expedition notes, described the events of 1908 in terms that struck him immediately as remarkably consistent with the instrumental evidence he had already gathered from Irkutsk and elsewhere, independent confirmation arriving from an entirely different kind of source that he was closing in on something real. The physical conditions of the journey itself were, by Kulik's own written account, punishing. Summer travel through the taiga meant navigating waterlogged ground that could swallow a loaded cart to its axle, crossing rivers swollen with snowmelt, and enduring dense clouds of mosquitoes and biting flies that emerged from the region's extensive wetlands in numbers thick enough to affect visibility. Members of the expedition reported losing significant body weight over the course of the journey, and at least one early attempt to reach the site had to be abandoned entirely after supplies ran critically low, well before the team came within sight of the fallen forest. It would take Kulik and his companions nearly 3 weeks of difficult overland travel simply to reach the outer edge of the blast zone from the nearest railway station, a journey that, more than a century later, can be covered by helicopter in a matter of hours. When Kulik finally reached high ground overlooking the affected area, what he saw exceeded anything the second-hand reports had prepared him for. Trees stretched to the horizon in every direction, all of them down, all of them stripped of branches, all of them pointing away from a single central region, as if some enormous hand had swept outward from one point across an area larger than a major city. Kulik, still operating under the assumption that he was looking for a crater, pushed his expedition toward the center of the devastation, expecting to find, at last, a hole in the ground and the meteorite that had made it. He found neither. At the center of the blast zone, Kulik discovered something that seemed, at first, to contradict everything he expected: a stand of trees still standing upright, though stripped bare and scorched, surrounded on all sides by trees that had been knocked flat and thrown outward. Nearby, several small, waterlogged depressions in the boggy ground briefly raised his hopes, circular basins that looked, to an eye eager to find one, remarkably like small impact craters. Kulik spent considerable effort probing and later attempting to drain one of these depressions, convinced it concealed fragments of the meteorite beneath layers of peat and permafrost, at one point diverting a significant portion of his limited expedition resources and remaining field season toward the effort. Later analysis, conducted using techniques unavailable in Kulik's lifetime, would determine that these depressions were not impact craters at all, but naturally occurring thermokarst formations, sinkholes created by the seasonal thawing and refreezing of ground ice, a common feature of Siberian permafrost terrain, entirely unrelated to the 1908 event. Similar formations can be found scattered throughout the wider region, in areas with no connection whatsoever to the blast, formed by the same slow freeze-thaw cycle acting on permafrost anywhere across the taiga. The crater Kulik searched for, across 4 separate expeditions spanning more than a decade, was never there to be found. In, out. What Kulik had stumbled onto, without fully realizing it, was the central clue to solving the mystery he had spent his career pursuing. The absence of a crater was not a gap in the evidence, it was the evidence. The standing trees at the center, later dubbed the telegraph pole trees for their stripped upright appearance, marked the point directly beneath the airburst, the one location where the shock wave, traveling almost straight downward, struck trunks with a force that snapped their branches and stripped their bark but lacked the lateral force needed to topple them entirely. Radiating outward from that point in every direction lay the felled forest, trees lying with their tops pointed away from the center in a pattern so precise that, decades later, researchers would use it to calculate both the altitude and force of the explosion with an accuracy Kulik himself never achieved. Kulik returned to the site on 3 further expeditions across the following decade, each one better equipped and more ambitious than the last. His second expedition, in 1928, brought a larger team and more substantial surveying equipment, allowing for the first systematic ground-level mapping of the fallen tree pattern across a significant portion of the blast zone. His 1929 expedition included, for the first time, aerial photography of the blast zone, captured from a small biplane, among the earliest uses of aerial survey photography anywhere in Soviet scientific research, and a technique that finally allowed him to appreciate the true scale and precise radial symmetry of the fallen forest in a way that ground-level observation alone could never have revealed. From the air, the pattern of fallen trees resolved into something unmistakable, a vast, roughly butterfly-shaped zone of destruction with the standing telegraph pole, trees marking its center, the whole formation stretching across an area that took the survey aircraft the better part of an hour to photograph in full. Even from the air, however, no crater presented itself, and no fragment of solid meteoric material was ever recovered from the site, despite years of dedicated searching. Kulik's final expedition to the region, delayed by a lack of funding and by the broader political pressures of the 1930s, took place in 1938 and again relied heavily on aerial photography, this time producing a far more complete photographic record than any previous attempt. By that point, nearly a full generation had lived and died since the explosion itself, and Kulik, now well into middle age, had spent more than a decade of his professional life on a search that had, by any conventional measure, failed to find what it originally set out to find. He remained, according to colleagues' later recollections, convinced almost to the end that a substantial buried mass of meteoric material still awaited discovery somewhere beneath the boggy ground of the blast zone. Kulik did not live to see the mystery resolved. He died in 1942, a prisoner of war during the Second World War, having spent the final 2 decades of his career defending, revising, and continuing to test a theory about a crater that later science would show never existed. His death came after he had volunteered for a militia unit defending Moscow against the German advance, despite being well past the age of standard military service, a decision colleagues later attributed to the same stubborn determination that had carried him through years of difficult expeditions into the Siberian wilderness. Much of his original expedition archive, including photographs and field notes from all 4 of his Tunguska expeditions, survived the war only because it had been transferred to secure storage in the Academy of Sciences collections well before the German invasion reached Moscow itself. Yet his expeditions produced something more valuable than the meteorite fragments he had hoped to find: the first systematic photographic and cartographic record of the blast zone, mapped tree by tree across hundreds of square kilometers at a time when the physical evidence was still relatively fresh and largely unaltered by decades of forest regrowth. Without that record, much of what later scientists would eventually piece together about the explosion's altitude, energy, and direction might never have been reconstructible at all. It would take Soviet scientists another 2 decades, using Kulik's original survey data alongside newer methods, to answer the question his expeditions had failed to resolve. If there was no crater and no surviving fragments of a solid meteorite, what exactly had exploded over the taiga? In 1958, a new Soviet expedition led by geochemist Kirill Florensky returned to the region, this time searching not for a crater, but for microscopic evidence, the kind of trace material that an airburst rather than a ground impact would be expected to leave behind. Florensky's approach reflected decades of accumulated understanding about how airbursts differ from ground impacts, understanding that had developed gradually across the mid-20th century as scientists studied both nuclear weapons testing and a small number of other confirmed meteor airbursts elsewhere in the world. Rather than searching the surface for visible fragments, as Kulik's expeditions had done, Florensky's team focused on a far more painstaking method, collecting soil and peat core samples from carefully chosen locations across the blast zone, then processing each sample back in the laboratory using magnetic separation, a technique that draws out any iron-rich particles from a much larger volume of ordinary soil, using a simple magnet passed repeatedly through a suspended slurry of the sample. The technique relies on a basic physical principle. Magnetite, one of the primary minerals expected in vaporized meteoric material, is strongly magnetic, while the vast majority of ordinary forest soil is not. By dissolving each sample into a liquid suspension and drawing a magnet slowly through it, technicians could isolate the small fraction of magnetically responsive particles from an otherwise overwhelming volume of ordinary organic and mineral material, reducing a full sample down to a residue small enough to examine individually under a microscope. The work was slow, repetitive, and mostly unglamorous, technicians spending entire seasons sorting through what amounted to little more than mud and peat, looking for particles smaller than a grain of sand. According to later accounts from members of the expedition, the first confirmed spherules were identified not in the field, but back in a laboratory in Moscow, months after the samples had been collected, when a technician examining a slide under magnification noticed a scattering of tiny, perfectly round particles, unlike anything expected in ordinary Siberian topsoil. It was, by most accounts, a quiet moment, rather than a dramatic one. No shout of discovery, just a technician pausing, looking again, and then asking a colleague to confirm what she was seeing. It was exactly the kind of careful, incremental labor that rarely makes for a dramatic expedition account, but that ultimately produced the single most important physical evidence anyone had recovered from the site in 50 years of searching. Sifting through soil and peat samples collected across the blast zone, Florensky's team identified thousands of tiny spherical particles, no larger than fractions of a millimeter, composed of magnetite and silicate material, with a chemical composition distinct from ordinary earth minerals. The density of these spherules was found to increase steadily as sampling locations moved closer to the center of the blast zone, forming a rough concentration gradient that matched with reasonable consistency the radial pattern of the fallen forest itself, further confirmation that the material had originated from a single point source above the center of the devastation, rather than arriving by some unrelated process. These microscopic spherules, later confirmed through more advanced chemical analysis in subsequent decades, are now understood to be the vaporized and resolidified remnants of the object itself, droplets of molten rock and metal flash frozen in the upper atmosphere during the object's catastrophic disintegration, then scattered across hundreds of kilometers as they settled slowly back to Earth over the following days and weeks. Under a microscope, these spherules show a distinctive layered internal structure, evidence of rapid cooling from an extremely high temperature consistent with material that had briefly existed as molten droplets suspended in the upper atmosphere before solidifying and falling back to the surface. It is in effect the closest thing to a fingerprint the Tunguska object left behind. Not a single mass of stone waiting to be found, but a fine, near-invisible rain of its own vaporized remains, scattered so widely and so thinly across the landscape that it evaded detection for exactly 50 years. The chemical composition of these spherules, along with the altitude, energy, and structural weakness implied by the airburst itself, has shaped the two leading explanations that scientists continue to weigh today. One holds that the object was a small asteroid, likely stony rather than metallic, its structure loose enough with internal fracturing to disintegrate under atmospheric stress before ever reaching the ground. Stony asteroids of this type, technically classified as chondrites, make up the large majority of confirmed meteorite falls studied on Earth and are understood to form from material that never experienced the intense heating and melting that shaped larger planetary bodies, effectively unaltered leftover material from the very earliest stages of the solar system's formation, roughly 4.6 billion years ago. The other leading explanation holds that the object was a fragment of a comet, composed largely of ice mixed with dust and rock, a structure that would explain both the airburst's altitude and the near-total absence of solid debris, since a body made significantly of ice would vaporize almost completely in the heat of its own destruction. Comets are generally understood to originate much farther from the Sun than asteroids in one of two distant reservoirs, the Kuiper Belt, a disc-shaped region of icy bodies beyond the orbit of Neptune, or the Oort cloud, a much more distant and roughly spherical shell of material thought to extend nearly a quarter of the way to the nearest neighboring star, a comet fragment large enough to produce the Tunguska explosion. Under this theory would have begun its journey toward Earth from one of these distant reservoirs, potentially millions of years before it ever arrived. Later research, drawing on more advanced isotopic analysis of the recovered spherules in the final decades of the 20th century, has tended to favor the stony asteroid explanation based on chemical ratios that align more closely with known asteroid compositions than with typical cometary material, though the match is imperfect enough that some researchers continue to favor a cometary origin, or even a hybrid explanation involving a body with mixed composition. This kind of isotopic analysis relies on measuring the precise ratios of different elemental isotopes present within a sample, variations too subtle to detect through ordinary chemical analysis, but reliably distinct between material that formed in different regions of the early solar system. Modern mass spectrometers, instruments capable of measuring these ratios down to parts per million or finer, have made it possible to compare Tunguska's microscopic spherules directly against the known isotopic signatures of well-studied meteorite falls elsewhere in the world, adding a layer of chemical precision to a debate that, for most of the 20th century, had to rely on far less exact comparisons. Some researchers have also proposed that the object may have been a rare and particularly fragile type of stony asteroid, one with an unusually high porosity that would make it structurally similar in some respects to a loosely packed rubble pile, rather than a single solid mass, a structure now known from direct spacecraft observation of several nearby asteroids in the 21st century to be considerably more common among small asteroids than scientists once assumed. Neither theory has been definitively confirmed, neither has been fully ruled out. More than a century after the event, The precise nature of the object that leveled 2,000 square kilometers of Siberian forest remains one of the open questions in planetary science, not because scientists lack the tools to investigate it, but because the object itself left behind so little to examine, having announced its arrival with light and heat and pressure and very little else. In the years that followed Kulik's expeditions, the forest did what forests do after even the most violent disturbance. It began, slowly and without ceremony, to heal itself. The recovery of the Tunguska blast zone has become, over the past century, one of the most closely studied examples of large-scale ecological succession following a natural disturbance anywhere on Earth. Unlike a wildfire, which consumes standing vegetation and leaves behind bare, blackened ground, the airburst had done something different. It had killed the forest by force rather than by fire, snapping trunks and stripping branches while leaving root systems, seed banks, and soil largely intact beneath the fallen wood. This distinction mattered enormously for what came next, since a forest with its underground root and seed structures still intact can often recover far more quickly than one that has lost its soil and seed bank entirely to fire. Ecologists studying disturbance recovery elsewhere in the world, following major windstorms, volcanic eruptions, or large-scale logging operations, have since used the Tunguska blast zone as something of a natural reference case, precisely because so little else about the disturbance interfered with the underlying soil chemistry and root structure that any recovering forest ultimately depends on. Within the first few growing seasons after 1908, according to Kulik's own observations during his 1927 expedition, young growth was already emerging through the tangle of fallen trunks, birch and willow, fast-growing pioneer species that thrive in open, sunlit ground and require little more than bare soil and light to take hold. These species are often the first to appear after any major forest disturbance, functioning as a kind of ecological bridge, stabilizing soil and creating shade and shelter that slower-growing species need in order to establish themselves. Their seeds, remarkably light and built to travel long distances on the wind, would have arrived at the blast zone from surrounding unaffected forest within the first year or two, drifting in over a landscape that had, for the first time in longer than any tree standing there could remember, been fully opened to direct sunlight reaching the ground. Birch in particular produces enormous numbers of seeds each year, small enough and light enough to be carried for kilometers by even a moderate wind, an evolutionary strategy suited exactly to opportunities like this one. Sudden, unpredictable openings in an otherwise closed and shaded forest canopy. A single mature birch tree can release well over 1 million seeds in a good year, the overwhelming majority of which will never find suitable ground to germinate. In an ordinary, undisturbed forest, that failure rate approaches total. Across 2,000 square kilometers of freshly opened, sunlit ground, however, even a very small percentage of successful germination was enough to blanket the blast zone in young growth within a remarkably short span of time. By the time Florensky's expedition returned in 1958, exactly 50 years after the event, much of the blast zone was covered in dense young forest, dominated by these early pioneer species, though the pattern of the original devastation was still faintly legible on the ground for anyone who knew how to look for it. Subtle variations in tree age and species composition, tracing the same radial pattern that the fallen trunks had traced half a century earlier. Members of Florensky's team, working alongside their soil sampling, took the opportunity to survey this new growth as well, producing some of the first detailed scientific documentation of how a taiga ecosystem recovers from a disturbance of this scale and suddenness. Their notes describe a forest already thick enough in places to make walking difficult, dense stands of young birch and pine standing 20 or more feet tall, growing directly out of ground still littered, here and there, with the slowly decaying remains of the original fallen trunks, half buried in moss and undergrowth after 50 years of accumulated organic material. Coniferous species, the pines, spruces, and larches that had dominated the forest before 1908, returned more slowly. These trees generally require the shelter of an already established canopy to germinate successfully, and so their return depended on the pioneer species that had come before them, a slow relay of one forest generation preparing the ground for the next. Siberian larch, the single most common conifer across much of this region, is itself a somewhat unusual tree among conifers in that it sheds its needles each autumn like a deciduous tree, an adaptation to the region's extreme winter cold that also, incidentally, means a larch-dominated forest floor receives considerably more seasonal sunlight than one dominated by evergreen spruce or pine, subtly influencing exactly which understory plants and young trees are able to establish themselves beneath it during the recovery process. Dendrochronologists, scientists who study the growth rings preserved within tree trunks, have since used core samples from surviving trees at the edge of the blast zone to build a detailed year-by-year record of the forest's recovery. Every tree adds a new ring of growth each year, its width varying with temperature, rainfall, and available sunlight, a natural, continuous record layered quietly inside the trunk of anything that survives long enough to keep growing. By comparing ring patterns from trees at the very edge of the blast zone, which survived the explosion itself, but were affected by the sudden change in surrounding light and canopy structure, researchers have been able to cross-reference ring width and density against known regional weather patterns, helping confirm the precise timeline first suggested by Kulik's early ground surveys, using evidence that had been growing, ring by ring, inside the surviving trees themselves the entire time. By the early 21st century, more than 100 years after the blast, botanists surveying the region found that much of the original taiga forest structure had been substantially restored, with young conifers now growing tall enough to begin reclaiming the canopy that pioneer birch and willow had held for decades. And yet, even with all of this recovery, the scar has never fully disappeared. Fungal networks in the soil, largely invisible but essential to how a forest recycles nutrients from dead and decaying wood, also had to re-establish themselves across the blast zone, feeding initially on the enormous volume of downed timber left behind by the shockwave. Mycologists studying similar disturbed forests elsewhere have found that this kind of sudden, massive influx of dead wood can temporarily reshape the balance of fungal species present in forest soil, favoring decomposer species suited to breaking down large quantities of timber over species more specialized for slower, ordinary leaf litter, a shift that, in the Tunguska case, likely persisted for several decades before the soil's fungal community gradually returned to something resembling its pre-1908 composition. Beneath the surface, the permafrost itself responded to the sudden loss of forest cover in its own slow, distinct way. Standing forest canopy normally shades and insulates the ground below it, keeping the underlying permafrost several degrees cooler than it would be if exposed to direct summer sunlight. The sudden removal of that canopy across 2,000 square kilometers likely caused a temporary deepening of the seasonal thaw layer in the years immediately following the blast, before the returning pioneer growth gradually restored enough shade to allow the ground to restabilize. Researchers studying permafrost dynamics elsewhere in the Arctic and subarctic have used the Tunguska blast zone as one of relatively few real-world examples of how quickly a disturbed permafrost landscape can recover once vegetation cover is restored, a question of growing scientific relevance as warming temperatures put pressure on permafrost regions across the globe for entirely unrelated reasons. Satellite imagery of the region, available since the latter half of the 20th century, still shows a faint but discernible pattern in forest density and species distribution across the old blast zone, a ghost of the original radial pattern, visible not to the eye on the ground, but from orbit in the subtle differences between 100-year-old secondary growth and the older untouched forest that surrounds it. Modern remote sensing techniques, using satellites capable of measuring subtle variations in vegetation density and canopy height across enormous areas, have made it possible to trace the outline of the original blast zone with a precision Kulik, working entirely on foot and by aerial photograph, could never have achieved. Some of these instruments can detect differences in forest canopy height of less than a meter from orbit, or measure the slightly different way that younger, more uniform secondary growth reflects near-infrared light compared to the more varied canopy of an older, undisturbed forest. Differences invisible to the human eye, but clear enough in the data to still trace the outline of an explosion more than 100 years after it occurred. It is a strange kind of permanence, the physical evidence of a catastrophic, near-instantaneous event, preserved not in stone or crater, but in the age and arrangement of trees, a signature written in wood and shadow that only distance and time can properly reveal. A forest remembers, in its own way, longer than most people expect. There is something worth sitting with in this quietly, in the space between one thought and the next. The energy released over the taiga that morning in 1908 was, by any measure, almost unimaginably violent, capable of leveling a modern city in the space of a few seconds. And yet the land itself, given enough time, absorbed that violence and returned, gradually, to something resembling stillness, not the same forest that existed before. Different in ways a trained eye can still detect more than a century later, but a forest nonetheless, growing quietly over ground that had briefly become the site of one of the largest natural explosions in recorded human history. In, out. The scale of time involved is worth pausing on for a moment. A human lifetime, even a long one, spans perhaps 80 or 90 years. The Tunguska forest has now been rebuilding itself for well over 100, and by most botanical estimates, it will take several more decades before the canopy fully returns to the density and composition it had before that June morning in 1908. Multiple human generations, born and grown old, in the time it has taken a single forest to quietly repair itself. Bayan himself, according to the fragments of testimony that survive him, lived well into old age, long enough to see the earliest pioneer growth rise well above head height across the land his family had once grazed, though the mature forest he had known as a young man would not fully return within even his own long lifetime. His grandchildren and their children after them would be the ones to eventually see something closer to a fully restored canopy, generations removed from the morning their ancestor first watched his reindeer scatter toward a threat he could not yet see. This is not a fast story. It never was. Beneath the speed of the explosion itself, the violence took less than a minute. The recovery has taken, and continues to take, longer than anyone who witnessed it firsthand was able to live to see completed. Ecologists refer to this entire sequence: bare ground, pioneer species, intermediate growth, and eventual return to a stable, mature forest community, as secondary succession, distinct from the much slower primary succession that occurs when life colonizes entirely bare rock or newly formed volcanic soil with no pre-existing seed bank or root structure to draw upon, because the Tunguska blast zone retained its underlying soil and root systems even after losing its standing trees. Its recovery has followed a considerably faster secondary succession pathway. One ecologists estimate might otherwise take twice as long or longer in a landscape that had lost its soil structure entirely to fire or erosion. Somewhere in that mismatch of timescales, a fireball crossing the sky in seconds, a shockwave circling the earth in hours, and a forest quietly rebuilding itself across more than a century, there is a kind of scale that is difficult for a single human perspective to fully hold. It is the same scale in miniature that governs so much of the physical universe: violent, sudden events, followed by long, patient, mostly invisible processes of return. Stars themselves follow a version of the same pattern, spending mere seconds in the catastrophic collapse of a supernova before settling into remnants that continue to evolve, expand, and interact with their surroundings for tens of thousands of years afterward. Consider for a moment how the basalt beneath the Tunguska forest itself came to be. It formed roughly 250 million years ago during a series of volcanic eruptions so vast and so sustained that they are thought to have lasted, in total, for close to 1 million years. Eruptions that released enough gas and ash into the atmosphere to have contributed to the most severe mass extinction event in the history of complex life on Earth, one that eliminated an estimated 90% of all marine species. That event, too, followed the same basic shape: violence measured in a geological instant, followed by recovery measured across an almost unimaginable stretch of time, life slowly finding its way back across millions of years, until, eventually, forests like this one could exist at all. Against that backdrop, a single explosion in 1908 and a single forest's recovery across a mere century becomes almost a small thing. Almost. It did not feel small to anyone who stood beneath the sky that morning. It does not feel small even now, considered slowly, one fact at a time, but scale is a strange thing to hold in the mind for very long, and perhaps it is enough, tonight, simply to notice it, and let it settle, the way dust settles, slowly, back toward the ground. The taiga does not remember 1908 as a date, or a mystery, or a scientific debate. It simply continues, tree by tree, season by season, the way it has for thousands of years before that morning, and will, in all likelihood, for thousands of years after every person currently alive has been forgotten. The wind moves through the young canopy the same way it always has. Rivers still wind through the same low valleys. Wildlife has returned in its own gradual way, following the same rhythm as the forest itself. Insects first, within the first year or two, then birds and small mammals drawn back by new sources of food and shelter as the pioneer growth thickened, and finally, slowly, larger animals following as the recovering forest began once again to offer the kind of cover and forage that a mature taiga ecosystem provides. Reindeer herds, similar to the ones Bayan once tended, still pass through parts of the old blast zone today, grazing on lichen and undergrowth across ground that more than a century ago briefly became one of the most violent places on the surface of the planet. Somewhere beneath the surface, in soil that has now absorbed and released more than a century of snow and thaw, faint traces of magnetite and silicate spherules remain, scattered and inert, the last physical remnants of an object whose exact origin is still not fully known. They will likely remain there, largely undisturbed, for a very long time to come. Even the spherules themselves are changing, very slowly. Buried in acidic, waterlogged peat, the tiny magnetite particles that Florensky's team first identified in 1958 are subject to slow chemical weathering, a process measured not in years, but in centuries. Some will eventually dissolve entirely. Others, protected by depth or by the specific mineral chemistry of the soil around them, may persist largely unchanged for thousands of years more, a faint chemical signature waiting in the ground for some future researcher working with instruments not yet invented to find and read again. Nothing about this is urgent. The forest is not in a hurry. It was not in a hurry 100 years ago, and it is not in a hurry now. Somewhere in that patience is a kind of lesson, though the forest itself is not offering one. It is simply doing what forests do, at the pace forests do it, indifferent to whether anyone is watching, indifferent to the century that has passed, indifferent to the name of the object that once fell toward it out of a clear June sky. It simply grows. The Tunguska Event did not remain a purely historical curiosity. In the decades since Florensky's spheral discoveries, it has become something more useful to modern science, a benchmark, a known quantity against which newer, smaller events can be measured and understood. On the morning of February 15, 2013, more than a century after the Siberian blast, a much smaller object entered Earth's atmosphere over the city of Chelyabinsk in the southern Ural region of Russia, roughly 1,500 kilometers west of the Tunguska site. It arrived just before sunrise local time at an even steeper, shallower entry angle than the Tunguska object, traveling at roughly 19 kilometers per second, faster than Tunguska's estimated speed, though carrying far less total mass and therefore far less total energy. Unlike the 1908 event, this one occurred in daylight over a populated area and was captured on video by dozens of dashboard cameras almost immediately after it occurred, a byproduct of a local custom of mounting cameras on vehicle dashboards, largely to document traffic disputes and insurance claims. That unrelated habit gave scientists something Tunguska never offered: direct, unambiguous visual evidence of an airburst as it happened, viewed from dozens of different angles simultaneously, allowing researchers to reconstruct the object's exact trajectory, speed, and breakup sequence with a level of precision no historical airburst had ever previously allowed. The Chelyabinsk object was far smaller than its Tunguska predecessor, estimated at roughly 20 meters across, compared to Tunguska's estimated 50 to 60 meters, and it exploded at a higher altitude, around 30 kilometers up, releasing energy equivalent to approximately 500 kilotons of TNT, still more than 25 times the energy of the Hiroshima bomb, but only a small fraction of Tunguska's estimated force. The resulting shock wave shattered windows across the city, injuring over 1,200 people, almost entirely from flying glass rather than direct blast effects, and offered scientists a rare, modern, closely instrumented dataset against which to test and refine the models they had built to explain the Siberian event more than a century earlier. The comparison proved remarkably useful. The airburst altitude, The radial pattern of overpressure damage, the characteristic sequence of blinding light, followed seconds later by shock wave and sound, all of it closely matched what researchers had spent decades reconstructing about Tunguska from indirect evidence alone. Chelyabinsk became, in effect, a smaller-scale confirmation of a theory built almost entirely from tree patterns, magnetic anomalies, and microscopic spherules. Where Kulik had spent years searching a remote forest for evidence of an event no instrument had directly recorded, Chelyabinsk arrived already documented in extraordinary detail, precise trajectory data calculated from dashcam footage, meteorite fragments recovered within days from a frozen lake, and infrasound recordings from monitoring stations around the world, all confirming within a matter of weeks what had taken Tunguska researchers the better part of a century to piece together. It also served as a pointed reminder that objects capable of this kind of destruction are not confined to the distant past. Public and institutional awareness of near-Earth object hazards has shifted considerably across the decades since Tunguska was first scientifically confirmed. For much of the 20th century, the subject remained largely confined to specialist academic circles, treated more as a curiosity of planetary science than as a matter of practical civil concern. That began to change gradually, starting in the 1980s and 1990s, as improved understanding of the role a large asteroid impact played in the extinction of the dinosaurs brought renewed scientific and public attention to impact hazards generally, followed by the observed 1994 collision of a fragmented comet with Jupiter, an event captured in unprecedented detail by telescopes and spacecraft alike, offering the public a vivid, undeniable demonstration that large-scale cosmic impacts were not merely theoretical. Research into the Tunguska event itself has never fully stopped, even now, more than 100 years on. New expeditions have continued to visit the site periodically since Florensky's era, applying each successive generation of scientific technique to the same forest and the same buried soil, ground-penetrating radar surveys, searching for any remaining buried fragments too deep for earlier researchers to detect, updated computer simulations modeling the object's likely entry angle and breakup sequence with far greater precision than was possible even a few decades ago, and continued isotopic analysis of the original Florensky spherules, using instruments sensitive enough to measure chemical signatures that simply could not have been detected in 1958. Each new study tends to narrow the range of remaining possibilities slightly, without yet closing the question entirely. A slow, incremental process not unlike the forest's own recovery, proceeding one careful measurement at a time across a span of years far longer than any single researcher's career. In response to Chelyabinsk, and building on decades of prior effort following Tunguska, international efforts to track near-Earth objects have expanded considerably. Survey programs operating today, using networks of ground-based telescopes scanning the sky nightly, have cataloged the majority of near-Earth asteroids large enough to cause continent-scale devastation, objects a kilometer or more across. These programs work by repeatedly imaging wide swaths of the night sky and comparing successive images to identify points of light that move against the fixed background of distant stars, a method that has, over several decades, identified and tracked the orbits of tens of thousands of previously unknown asteroids. Dedicated observatories in Hawaii, Arizona, and Chile now scan large portions of the visible night sky on a near-continuous basis specifically for this purpose, feeding their observations into shared international databases that allow newly detected objects to be cross-checked, confirmed, and tracked by multiple institutions within hours of an initial sighting. Amateur astronomers, too, contribute meaningfully to this effort. A global network of hobbyist observers, using increasingly capable consumer telescopes, regularly assist professional survey programs by providing follow-up observations that help confirm and refine the orbits of newly detected objects, extending the effective reach of a detection system that no single institution could staff and fund entirely on its own. A space-based infrared survey telescope, launched specifically to search for near-Earth objects that are difficult to detect using visible light alone, has added further coverage, particularly for darker, less reflective asteroids that ground-based optical telescopes are more likely to miss entirely. Together, these efforts represent a scale of systematic sky monitoring that did not exist in any form at the time of the Chelyabinsk event, let alone in 1908. Objects in the range of Tunguska's estimated size, however, remain considerably harder to detect. Their smaller size, combined with the sheer number of them believed to exist, means that many such objects are only discovered after a close pass, or in some cases, not detected at all before entering the atmosphere, as was the case with the object over Chelyabinsk, which arrived from a direction relative to the Sun that made it effectively invisible to ground-based telescopes until it was already inside the atmosphere. Objects approaching from roughly the same direction as the Sun remain, even with modern instrumentation, one of the most persistent blind spots in near-Earth object detection, since no ground-based telescope can observe effectively in the direction of daytime sky glare. Proposed space-based telescopes, positioned to observe from an angle that would eliminate this particular blind spot entirely, remain in various stages of planning and development, a reminder that even the most well-funded modern detection efforts still carry meaningful gaps more than a century after the first attempt to understand what had happened over the Siberian taiga. In the days following the Chelyabinsk airburst, search teams recovered numerous small meteorite fragments across the surrounding countryside, the largest and most significant of which, a chunk weighing over half a ton, was eventually recovered from the bottom of a nearby lake where it had punched a clean hole through the winter ice upon landing. Chemical analysis of these recovered fragments confirmed the object as an ordinary chondrite, the same broad category of stony asteroid that remains the leading candidate for the composition of the much larger Tunguska object, offering an unusually direct physical point of comparison between the two events, separated by more than 100 years and a considerable difference in scale. Current estimates suggest that an event on the scale of Tunguska occurs, on average, roughly once every few hundred years, though the irregular and unpredictable nature of near-Earth object orbits makes any such estimate necessarily approximate. Scientists classify near-Earth objects into several broad size categories, partly because the risk each category poses and the detection challenge each presents differs so substantially. Objects a kilometer or more across, capable of causing global climate disruption on top of direct destruction, are now believed to be almost entirely cataloged. Objects in the 100 to 500 meter range, capable of regional devastation, remain only partially cataloged, and objects in Tunguska's estimated size range, capable of leveling a city-sized area, but too small and too numerous to track completely with current technology, remain the least well understood of the three, precisely the category into which both the Tunguska and Chelyabinsk objects fell. Roughly 70% of Earth's surface is covered by ocean, and much of the remaining land consists of desert, polar ice and other sparsely inhabited terrain, meaning that, statistically, an airburst of this size is considerably more likely to occur somewhere with few or no witnesses than directly above a major population center. Most of Earth's surface remains ocean or sparsely inhabited land, meaning that when the next Tunguska-scale airburst does occur, there remains a meaningful chance it will happen, as the 1908 event did, over a remote or largely unpopulated region. It is worth sitting with the fact that it might not. Modern planetary defense research, still in its early stages, has begun testing methods for detecting and, in principle, deflecting hazardous objects long before they approach Earth. Missions launched in the past several years have successfully demonstrated the ability to alter the trajectory of an asteroid through direct kinetic impact, a spacecraft deliberately colliding with a small asteroid at high velocity, transferring enough momentum to measurably shift its orbital path. A proof of concept that would have been the subject of speculative science fiction in Kulik's era and is now a matter of active, ongoing engineering. The target chosen for this first test was not a hazardous object itself, but a small moonlet orbiting a larger, harmless asteroid, selected specifically because its orbital period around its companion could be measured precisely enough before and after the impact to detect even a very small change caused by the collision. The spacecraft itself, roughly the size of a small vending machine, struck its target at a relative speed of more than 6 kilometers per second, a deliberate, controlled collision monitored in real time by a trailing companion craft that captured images of the impact and its immediate aftermath, along with observatories on Earth that tracked the resulting change in the moonlet's orbital period in the weeks that followed. Follow-up observations of that same asteroid, conducted in the years since, confirmed that the shift in trajectory persisted well beyond the initial impact, suggesting that a similar technique, applied early enough and to a sufficiently small object, could in principle prevent an impact entirely rather than simply reduce its severity. None of this diminishes the strangeness of what happened over the Siberian taiga on that June morning in 1908. If anything, it sharpens it. An event large enough to level a modern metropolitan area, powerful enough to circle the globe twice in the form of a pressure wave, and violent enough to scorch reindeer herds and startle Evenki families from their homes 30 kilometers away, occurred without a single confirmed human death, in one of the only places on Earth remote enough to absorb it without catastrophic loss of life. There is no way to know with certainty whether that was chance or whether it was simply the very long odds of a very large planet playing out exactly as they should. Every measurement scientists have taken across more than a century of study, every fallen tree, every magnetite spheral, every bar graph reading and dashcam frame from Chelyabinsk, has been an attempt to answer a single, deceptively simple question: what exactly happened? And after all of that careful, patient work, the honest answer remains only partially complete. Enough is known to say with confidence that it was real, that it was an airburst, and that its energy output places it among the largest natural explosions ever measured on the planet. What remains unknown is smaller in scope, but no less stubborn: the precise nature of the object itself, still waiting, perhaps, for some future piece of evidence not yet discovered. Consider for a moment what a comparable event would mean for a major modern city. An airburst releasing 10 to 15 megatons of energy directly above a densely populated urban area would be expected to cause catastrophic structural damage across a radius of many kilometers, with casualties potentially reaching into the hundreds of thousands, depending on the specific altitude and location of the detonation. Modern blast modeling software, originally developed to study the effects of nuclear weapons, has been used by several research groups specifically to simulate a Tunguska-scale airburst occurring over various real cities, producing damage estimates intended less to alarm than to inform ongoing civil defense and emergency planning discussions, most of which remain even now in a fairly early and exploratory stage. That such an event instead occurred over one of the most sparsely populated stretches of land on the entire planet remains, more than a century later, a matter of simple, undeniable good fortune, unconnected to any particular effort or intention on the part of anyone involved. The forest has grown back, the spherules remain quietly buried in the soil. The precise identity of the object, asteroid or comet, stone or ice, remains, even now, an open question that new research continues, slowly, to narrow. Bayan's own descendants, according to the researchers who first recorded his account decades after the event, continued herding reindeer across parts of the same wider region well into the 20th century. Their family's knowledge of the land passed down the same way it always had been, through observation, repetition, and the slow accumulation of experience across generations. Whatever they came to believe about the strange morning their ancestor had witnessed, the land itself simply continued on beneath them, indifferent to explanation, exactly as it continues on today. And somewhere above, unseen and largely uncatalogued, other objects of similar size almost certainly continue to orbit the sun, following paths that intersect, however rarely, with the orbit of Earth, paths that no one, even now, can predict with complete certainty. That too is simply how a solar system this old and this vast tends to behave. Small, quiet things are happening constantly, all around, that no one is watching closely enough to notice. A telescope somewhere is scanning the sky tonight, the way it does every clear night, cataloging faint points of light that may or may not turn out to matter. A researcher somewhere is looking once again at a decades-old photograph of a Siberian forest, checking a measurement against a newer model, adding one more small piece to a puzzle that began in 1908 and has still not been fully solved. Somewhere in Siberia, wind moves through a forest that does not know and does not need to know what happened to it more than 100 years ago. And somewhere far above all of it, quietly, patiently, the solar system continues turning, exactly as it always has. This has been the story of the Tunguska Event, brought to you by Quiet Science at Bedtime. If tonight's story helped you drift towards sleep, a like and a subscribe helps this channel keep bringing you more stories like it, and turning on notifications means you will not miss the next one. Everything you heard tonight is real. The Tunguska forest is out there right now, quietly growing back beneath a Siberian sky. Sleep well.